now, and we very much hope that we'll continue. But that depends on how well we perform, I guess. So we are being evaluated as well as. And since Matt is here, I just wanted to recap our history very briefly within a few minutes. Some of you were around back then, but basically we had the inauguration 3 years ago. It was 3 years minus a month ago. And Stephen Hawking came to that inauguration. Basically what happened was that I saw him a year earlier when we started contemplating the BHI. And I was visiting the Royal Society in London, and the caretaker of Stephen said, you know, Stephen is bored, nobody is speaking to him, would you mind speaking to him, please? And I said, okay. So I approached him, and obviously I didn't expect a reply. I said, we are planning to establish the Black Hole Initiative, the only center in the world that focuses on black holes at Harvard University within a year or so, and we would love it if you were to come for the inauguration. And of course I didn't wait for a reply, because it would have taken him 5 minutes to say yes or no. So I didn't expect too much, but then in January, just half a year later, Andy Strominger comes to my office and says, I just came back from Cambridge, England, and something amazing happened. And he was collaborating with Stephen. Stephen said to his doctor that he wants to come for the inauguration of the Black Hole Initiative. And the doctor always said no for 3 years already for any international travel, but on this occasion, he said yes. Because Stephen worked for a whole day crafting this letter. And he said, that's amazing, you know, that he allowed him, but the only problem, the only rub, is that it would cost $500,000. So now that's your problem. Try and deal with it. So I called the dean at Harvard, dean of science, the one that was before the one we will meet this afternoon. And he said, forget about it. I said, well, can we have some public lecture that will fund his visit? And he said, no way. You need the business model, and we will not be liable to his health. Just forget about it. So I hung up the phone, but then I remember that a few days later I'm supposed to visit in Palo Alto a very wealthy individual to whom I suggested that he will fund this visit, and he agreed. So that's how we got Stephen to come. Of course, back then we had no money whatsoever, so we couldn't even. And then we had the inauguration, and that was 2 years or so, 3 years ago at the inauguration, but then the operation started. Harvard gave us very nicely, very generously, this space, which is one of the nicest at Harvard, and we started the operation 2.5 years ago. And so now it was for 3 years, and as far as I'm concerned, and anyone can say what they think, but it's a great success. And my measure of success is how happy Ramesh is.
You've never seen me unhappy or
yes.
You have. So, serious testimonial here. Yeah.
No, because truly, I mean, Ramesh was department chair well before me, the astronomy department, and you know, he approached black holes in the sense that he studied black holes, but also lost his hair during that process of being department chair, just like black holes have no hair. But I can see how happy Ramesh is in this environment, and he's sort of like a canary in a coal mine. That he tells me that this place is doing very well. Ramesh goes to all the Monday philosophy sessions, right? And Peter can testify. Where is over there? We have established what I call a collaboration, in the sense that people from different disciplines come together. In fact, Faraz and I are writing my first paper in a philosophy journal right now. So that's the testimony. I remember still the very first seminar where Andy Strominger raised his hand and asked, what is an AGN? By now, these questions do not come up anymore. I think we speak the same vocabulary. There was an early concern that I had that it will be just like this temple of Babel, where sorry,
Tower
of Babel, yes, where people came with different languages. Nothing came out of this project as a result. I mean, or languages were mixed, so that nothing will come out because they were arrogant. At any event, people here are. Some of them are arrogant, but nevertheless, a common language was developed, and I think objectively speaking, we're doing very well. And it's really a great pleasure, intellectual pleasure, to interact with all of you, and I'm sure that everyone has that sense, and we very much hope to continue into the future. And with that, perhaps we'll introduce, is Fabio the first speaker? Oh, so one comment about Fabio. Fabio accepted our offer for a postdoc fellowship next year, so he will be here for the next 3 years, and he's just visiting us as a courtesy to give us a hint as to what excites him. He's also interested in communicating to the public science, and he produced beautiful videos on black holes, and I think I showed one of them last year, and you have a new one also.
It's a couple of them coming up.
Couple of them.
Next few months.
And where will people find them? Just
It's
in case.
TED.
So it's called TED for Education, TED Ed. So Fabio was at Yale for several years, and he will join us starting September 1st.
Well, with that, let me introduce Fabio to you. I said most of the things I wanted to say. Fabio is a graduate with a PhD from Scuola Normale Superiore in Pisa in Italy in 2016. Since then, he's been at Yale University as a postdoctoral fellow before briefly moving to Groningen in the Netherlands for a while. And for his PhD work, he was awarded 2 awards, one of them from the International Astronomical Union. But he's not here to talk about that work, which was of black hole seeds at very high redshift and how supermassive black holes form. Today he's talking about his more recent work on lensed quasars. Would Avi come in, please?
Yes. So thank you for the introduction, and thank you for having me here. Especially as Fabio was saying, it's a big pleasure for me to be here, also because I'm starting to work here in a few months. So today I'm going to talk about phantom quasars, or potentially missing populations of lensed high redshift quasars. So I thought it would be interesting to start with an historical introduction on the problem and issue of lensed quasar in the high redshift universe. And then I will talk about the detection of the first lensed quasar in the epoch organization, to which I also participated, and it was a paper by Fan from Arizona. And then most of my talk will be related to the theoretical consequences of this discovery, and there are also some updates on a paper that we're working right now at the end of this talk. So I thought it would be interesting to start with this curiosity. It's the first occurrence of the words lensed quasar on the AES. We're back on the 1971, so a few years ago. And this paper, in particular, I want to draw your attention to this part of the abstract, which says that quasars are not noble constituents of the universe, but merely bright compact objects, which have been focused and have had their brightness intensified by a galaxy situated along the line of sight, acting a gravitational lens. So this means that in 1971, of course, they still didn't believe that quasars were real noble constituents of the universe, but were just normal galaxies, lucky enough to be on the same line of sight on another foreground galaxy, and their intensity was magnified for that reason. So we arrived in 1971 with the discovery of the first lensed quasar, with this very famous paper by Walsh and collaborators. And in particular, they detected a quasar redshift 1.4, so sufficiently distant, and the separation between the two components was 5.7 arc seconds, so pretty far away with compared to the standards that I'll be talking later on in the talk. And here on the right, you can see the two spectra coming from the two images of the same quasar. And you can see they're basically the same, so that they understood that those two components were actually two images of the same faraway source. So of course, people started to think theoretically also about these papers, and at the beginning of the 90s, in the 92, 94, Pei, for instance, developed some of the first models of the probability of magnification. So the question now is, how likely is that high redshift quasars are magnified, and to which magnification factors? And they were also starting to understand that our view of the very early universe, so the very distant universe, can be fooled to some extent, so can be modified by the presence of galaxies close by to us. So the combined effect of gravitational lens can affect the way we see at the early universe. For instance, in this plot, you can see the quasar luminosity function, and in the bright end, so for very bright object, the presence of gravitational lensing can affect the slope of the bright end there. So we're in the beginning of the 2000, and with this famous paper by Whiting and Lev, people started to understand that it's actually very likely that high redshift quasars are magnified by intervening gravitational lenses. And in particular, they suggested that up to 1/3, so many quasars at redshift higher than 6, can be magnified by magnification factors up to 10, so strongly magnified. Just a reminder that we talk usually about strong lensing for magnification factors up to 2, so you can have several images in that case. So until a few months ago, this quasar at redshift 4.8 was the farthest away lens the quasar ever discovered, and in particular was, as I said, a redshift almost 5, and with a total magnification of about 3, so still strongly lensed. You can see a couple of images there, but not as lensed as the one that I'm going to talk about in a few seconds. So, as I said, this was true until a few months ago, when actually exactly 1 year ago now, we discovered it in March of 2018, when we discovered this quasar at redshift 6.5. So this is the first lensed quasar well inside the epoch of realization. And this amazing source has the maximum separation between the two components is about 0.2 arc seconds, so they're very, very close to each other, almost unresolved with the HST. And what is extraordinary about this source is that the magnification factor in this case is about 51. So this is what it's usually named an extremely magnified source. So let's see the different observations that we did. This is a preliminary observation with the LBT, so on the ground. And as you can see, you can't really tell that this source is magnified in this case. The source appears unresolved. You can see some asymmetry there on the east part of this, maybe, but you can't really tell. But what is very interesting about this source since the first observation is that it was ultraluminous. Actually, at detection, this quasar was by far the brightest source ever discovered in the universe. In fact, in this plot, you can see the estimated black hole mass here, and on the vertical axis, you see the volumetric luminosity. This is our quasar, and as you can see, it's about 2 times brighter than the brightest quasar found to that date, the Wu et al. 2015. So this was obviously a very, very interesting source, and we reported in this plot also other famous quasars. For instance, the Bañados et al. 2018 is the farthest away, it's redshift 7.54. And it's also interesting to note in this plot that these dashed lines here indicate fraction of the Eddington luminosity, meaning that a source accreting on this line is shining at the Eddington luminosity, instead going down they're shining at lower luminosities. This is interesting because, as you can see, this quasar appears to be shining at super Eddington luminosities, and this is not very common. I mean, we have some cases of super Eddington accretors in the Redshift universe, but this was accreting at strongly super Eddington luminosities. So, with a bolometric luminosity of about 3 in 10 to the 48 Hz per second and an estimated mass of about 5 billion solar masses, this source was extremely unusual. So we took a spectrum, of course. This is, at least part is a Keck spectrum. You can see, for instance, the magnesium line here, with which we estimated the spectroscopic redshift of the source. But for our purposes, what's really interesting in this source is this part here, shorter than the Lyman alpha. So let's take a look at that part in particular. Let's zoom in. And here you can see some high GM spikes. Basically, these are frequencies at which you can still see the light from the quasar, because the IGM, so the intergalactic medium, is not extremely deep at that regions in that at that frequencies, and then the light from the quasar can still pass through. But here, this is the deepest part of the Gunn-Peterson trough, meaning that the optical depth of the intergalactic medium is extremely large at those wavelengths, at those frequencies, meaning that in this part of the spectrum, you shouldn't be observing any light coming from the quasar. But actually, what we see is that we can observe a weak continuum emission in this part of the spectrum, and we know that it can't come from the quasar because no light from the quasar should be observed. So this triggered an additional interest to this source. So we took an HST image of this source, and this was really surprising to us. So what you can see here is that the central source, so the main emitter of light, is composed of 3 different components that we call A and B. And as you can see, they are kind of detached. So you can see some structure here. And here on the east part of the image, you can also see probably an additional component here that we call G. And we called it G because we believe this is the lens galaxy. This is actually lensing this source that is much farther away. So why we believe that this is the galaxy? Well, we can do the same, the following experiment. We can take an image of the same patch of the sky with a narrowband filter here in the deepest part of the Gunn-Peterson trough. So if we image in this region of the wavelength, we are sure that we are not observing the quasar because the intergalactic medium is extremely deep at those regions. And so we cut out completely the quasar that in fact disappears, and we remain with this source here, that it must be at lower redshift, a redshift lower than 6, because otherwise we couldn't image it. So we ended up with this best fit model in which we have a very far away quasar, redshift 6.51, and I want to point out that that determination of the redshift is very precise because it's a spectroscopic redshift, while the component is actually acting as a gravitational lens and is magnifying that source by 51, is a small galaxy at redshift approximately 0.7, and this is a photometric redshift, so meaning that the properties of the lens galaxy are less constrained than the properties of the quasar. So this is again the best fit model. So for the source we have a total magnification of about 51, and the maximum separation between the 2 components, the best fit model reports 3 components, but we can't really see the 3rd one, so we are trying to do some higher resolution observation now to actually check that the best fit model is the correct one. And as I said, the maximum separation is about 0.2 arc-second. Also, the lens galaxy is very peculiar because it's a very small galaxy. It's about in stellar mass 10 to the 10 solar masses. So this is actually the smallest lens galaxy that has ever been found to act as a gravitational lens. So now that we know that this source is magnified by a factor 51, we can shift this point to take into account the magnification.
Fabio,
Yes.
is this object bright enough for ground-based AO observations?
We're trying to do
You're trying to do that?
with the VLT. Yes.
VLT, okay.
Yes, and that's that we really hope that with the VLT and adaptive optics we'll be
Right.
able to detect the third component if it's true.
Would it also be suitable for the gravity experiment?
Gravity, I'm not sure about
It's
that.
too faint.
Is it too faint? That's
Yeah,
my
they
question.
need
How
the-
bright is this?
Uh,
What's the magnitude?
They need
They need 19, I thought.
no 14 or
well,
14
it's
or 12.
I'm not sure about the magnitude. To be honest, I don't
But
really
the
recall
Redshift.
the what.
You-
I don't recall the exact number of the magnitude right now, but
Okay.
I can check it later and I'll let you know.
Excuse me, that magnification of order 50 and then the redshift of the source and lens, how they are connected? I want to know, is there any other possibility that you have other galaxy, you see what I mean? I mean, how much this special magnification depends on the source redshift and lens redshift? You have
Well,
any
then-
formula to show us?
Yeah, well, what we can say is that this is the redshift that we expect for a typical lens galaxy to act as an optimal gravitational lens, because it's if you make the calculation, it's kind of midway between us and redshift 6.5. Okay, so redshift 0.7, approximately optimal gravitational lenses are between redshift 0.5 and 1.5. So this is in the range. So the calculation of the exact magnification, so 51, comes from a quite complicated. I didn't do directly the lens model, but what happens here is that this is the calculated fiducial model. So the model reproduces the components that we see in the HST image. Then the real image and the reconstructed image are compared to each other, and we see what is the best fit model that reproduces the reality, and we get it with a magnification about 51 and with all the other parameters considered.
But have you seen such a galaxy at this redshift? Have you observed it, or it's just model?
No, it's the galaxy that is shown here. I mean, you can probably see just a part of it because it's a very faint galaxy, you know. So it's very hard to get an image or a better constraint of the properties of this galaxy because it's very faint, and also taking away the quasar by applying the narrow band filter, you also probably take away a part of the light of the galaxy. So getting a clear image of the galaxy is quite hard so far. So I was saying, yes, if we take into account the magnification factor of 51, then this source is shifted within the known distribution of in bolometric luminosity in black hole mass, and we also reassured about the fact that this source is no more accreting at super Eddington accretion rate, but is accreting slightly below Eddington. So the final estimate for the bolometric luminosity is about 5 in 10 to the 46 per second, which is more reasonable, and also the black hole mass is about 500 million solar masses, which is still very big, but more reasonable than the previous calculation. So what we did with AVI is to compute probabilities of magnification. So we wanted to understand how likely it is to have such large magnifications at high redshift, and also if it's possible that we are missing a population of objects with slightly lower magnifications. So I will progressively fill up this plot. In particular, on the horizontal axis you have the total magnification, and on the vertical axis you have the probability of having a magnification factor higher than this value. So we know that our quasar is here with our magnification of about 51, and as this is the only quasar redshift higher than 6 that is found to be lensed out of 150 that have been found so far, this is the observed frequency of lensed high redshift quasar. So we did our model, and the model is based on the Pei formalism that I mentioned before. Galaxies are modeled as truncated single isothermal sphere, and now we need to assign properties to the galaxies, and we model it with galaxy luminosity function and velocity dispersion distribution following these papers. Of course, I don't have time now to go into details of the model, but feel free to ask me whatever you're interested in. But the main point is that the quasar luminosity function is modeled as a double power law, and the right-hand slope is modeled by beta, and this will be helpful with the following slides. So we're back here, and we want to calculate what is the probability distribution for different values of beta, the slope of the quasar luminosity function. So with a shallow value of beta, about 2.8, this is the probability distribution that we get, and in particular we get a strong lensing probability. As a reminder, strong lensing means magnification factor higher than 2, so this is a probability of about 4% of getting a strong lensing probability. Now we can get a steeper value of beta, about 3.6, and we get a higher probability, so about 20% of having a strong lensing case. What really matters in this plot is that independently on the slope of the quasar luminosity function, we do expect many more sources that have magnification factor lower than 10, as you can see from here, than the single one that we discovered so far. So these are what we're calling phantom quasars. So all these quasars that we know from the same distribution of galaxies that we know are out there, they should be lensed, especially at low magnification factors, but we can't really see them.
Is this assuming that the lensing population is between 0.5 and 1.5, as you mentioned earlier?
Hmm?
Is this assuming that the lensing population is between 1.5 and 1.5 redshift, as you mentioned earlier?
No, and we're not limiting our lensing population between 1 and 1.5. It can be up to the redshift of the source, of course. The problem is that the closer you get to the source, so the faraway source, the lower is the probability of actually getting a reasonable magnification. So why can't we see them? Well, we proposed, we found two different solutions to this problem. One is it could be a selection bias in photometric surveys against lensed quasars, and I'll be clearer in a few seconds. And the second is that the separation between the images is unresolved, even with the HST, so you can't really tell that this source is magnified because you can't see the second image.
Excuse me, can you go back to the previous slide to another one? So where is the redshift here? It should be more than 6, right?
Yes, this is.
But what is the probability if you are closer?
In this case, these lines are calculated exactly at redshift 6.5. So between redshift 6 and 7, it doesn't change very much. The time is very short. But of course, if you go down in redshift, the probability decreases because you have many more lenses at that point. You know. So going down in redshift, you have a lower number of galaxies that can act as a gravitational lens, and this is especially true when you go down to 1. So
but then it also competes because mu also decrease. So again, there is a competition between having less magnification and higher probability. You are in the tail of probability, right?
It's true.
So then the question is that why nobody has seen them? Because they are closer, so it's better to see them, and the probability goes up.
The probability goes up, but the problem is that, as I will show in a few seconds, it's likely that these sources are not identified in photometric surveys. Because how do you look for quasars? Basically, you make a photometric survey and you look for sources that you can see after the Lyman alpha, but you can't see in the dropout. So you actually are looking for dropouts after the Lyman alpha. But if these sources are not visible in this way, then you can't really select them as candidate quasars, and then you don't look for them. Like you don't worry about that. And that, depending on the cutoff in the redshift that you make, as you were mentioning, it can change things quite a lot. So why can be misclassified, as I was saying? So let's suggest that we're making a photometric survey. This is our high redshift quasar, if you are wondering. And so basically what you get, if you take a spectrum, of course, is that to select that source as a quasar candidate, you need to have a very strong dropout in the dropout band here compared to the emission before the Lyman alpha. But the problem is that if you have a galaxy in the same light of sight, in the same photometric area, then this introduces some flux into the photometric dropout there, and then this can fool the photometric selection criterion for the quasar. Also, I wanted to point out that if this source was, this is the spectrum of our quasar, if this source was magnified by less than 50, then what happens is that the ratio between the light of the quasar and the light of the dropout band would quickly fall, and this would increase the probability of misclassifying high redshift lensed quasars into low redshift galaxies. The second reason that I was mentioning is that the separation could be unresolved. So in this plot, I am showing the separation, the fraction of sources with components separated more than a value here in arcsecond. And remember, this is a cumulative plot. And here you can see our quasar with a separation of about 0.2 arcsecond, and this is the HST resolution limit. And as you can see, there are some sources here that we expect to have a separation below the resolution limit of the HST. So that means that even if we observe them, we cannot actually tell that they have multiple images. So in this case, W first could be the solution with a resolution comparable to the HST and a very large coverage. W first could be able to separate the lens from the background quasar. And here in this plot, in this image, I compared the PSF of W first with our image, and as you can see, W first should act as a ghostbuster in this case. So very briefly, how many phantom quasars are out there? So comparing basically the predicted probability of lensed quasar with the observed probability of lensed quasar, we can define the lensing boost factor, and this means basically this describes the amount of the unknown population as a fraction of the known population. Meaning, for instance, 0.5 means that the unknown population is 50% of the known population. So, very quickly, assuming a number density of high redshift source of high redshift quasar about 100 per gigaparsec cube, depending on the slope of the quasar luminosity function, with shallow values we can get an additional contribution about 3 per gigaparsec, which is very small, it's basically negligible. But with very large, very steep values, we could have up to about 1200 per gigaparsec, meaning that it's an incredible contribution to the early development of the early universe. So, I have maybe another minute to just discuss this last thing that we are doing. So we can ask at this point, what if the brightest high redshift quasars are lensed? So I will skip this, and we know that there is a problem in the redshift universe, as we are observing quasars, so supermassive black holes in the 10 to the 9 solar masses, already at redshift 7. In order to form these sources, we need to start from black hole seeds, so smaller units formed between redshift 20 and 30, and depending on the model, on the 10 to the 2 or 10 to the 5 solar mass scale. The problem is that the time between the formation and the observation of these sources is very short, it's about 500 million years, so we don't really know how to form these sources. But what if some of these sources are slightly magnified, even with magnification factor pretty low? This is not a crazy idea. Already Charles Keaton in 2005 suggested that up to 20% of all strongly lensed quasars at redshift higher than 6 could be missing a second detectable component. So what we are doing now is that we are basically demagnifying the black hole mass function. I won't go into details now as I'm running out of time, but we are trying to understand how does gravitational lensing affect the distribution of quasars over mass and over time. So let's see over mass. So what we are doing is basically we start from the luminosity function, we demagnify the luminosity function, and we go from the luminosity function to the mass function. So this is the observed black hole mass function at redshift 6, and now we demagnify this black hole mass function, assuming different values of the slope. And as you can see, going at steeper values, the difference becomes important. And for instance, at 10 to the 9 solar masses approximately, let's make it quick, what happens is that the number density of these sources is about 10 times lower than what we expected. We can do the same stuff in the same thing in the last 20 seconds, and we can study the development of quasars over cosmic time. You can see the epoch of quasars here, basically. This plot is taken from Wang. You can see a different error bar here because it's a different data set. We do the same thing that we did before, and we can ask what is the number density of quasars for which we can get only one quasar in the entire observable universe. So, as you can see here, we expect that reaching redshift 8, between 8 and 9, we will have only one quasar left in the universe. We can do the same thing that we did before, and we demagnify this distribution of quasars. And as you can see, with very steep values of the quasar luminosity function, we expect to be observing basically the last quasar in the universe earlier in the development. So as a reference, this is the farthest quasar ever found in the universe. So I'm sorry if I'm a couple of minutes late, and I'll leave you with my survey and I'll take your questions. Thank you.
A couple of minutes for questions.
Does weak lensing also affect our census of quasars and their properties?
Well, it depends on how, weak lensing meaning with a magnification factor lower than 2, you mean? Not as much as gravitational or strong lensing, because the difference in that case with the determination of the mass would be smaller, of course, but we haven't looked into weak lensing. We haven't looked even into micro lensing. That's something that I was thinking about adding in the model. So, for instance, micro lensing with stars in the lens galaxy, etc. But it's just a smaller addition to the model.
So, for the thing you mentioned at the end, where the high redshift quasars could be lensed, as in they could appear or could be appearing at lower redshifts, I guess. At some point, if you then require those black holes to become bigger at lower redshifts, at which point would you think you should be able to observe those black holes growing as through gravitational wave observations?
Well, so if I understand your question correctly, yes, let's assume that the oldest population of quasars is actually lensed, so the mass scale is lower than the one that we actually believe. Then we should observe also a shift in the gravitational wave way to actually have a look at this. Well, I haven't thought about it yet, but I don't believe that the highest redshift quasars are so much lensed that it would change dramatically their mass scale. So I still believe that they are very large black holes. I'm not talking about magnification factor of 50 that would automatically solve the problem, but at those redshift, even redshift 7, even a factor 2 in magnification would be very important toward the actual possibility of forming these sources. Because if you start, as I was showing here, if you start I haven't had the time to mention this, but in this maximal master Redshift 6, I did a very simple calculation. So you start at Redshift 25, which is kind of when we expect the black hole seeds to be formed. You start from a POP3 seed, meaning about 100 solar masses, and you allow it to grow for the entire cosmic time until Redshift 6 at the Eddington rate, so the maximal kind of maximal accretion rate, and you end up with this mass is about 9.3 in log. So it means that it's not impossible to form these sources. By Redshift 6, it's very unlikely that these sources can accrete for the entire cosmic time because you need to fuel them.
Yeah.
So to answer your question, I'm not sure, I don't know about the implications for LIGO, but it's
No, so this would not be for LIGO. So this would be observations with pulsar timing arrays.
Yeah.
But so those the black holes at the maximum mass might be too merging at too low frequencies even for PTAs.
yeah.
But
So
there might be some interesting
yeah.
cross checks to do.
No, it's true, because if you have a sufficiently high magnification factors that affect most of the quasar population on that redshift, then you should be observing also a shift in the gravitational redshift of the peak in which you observe them. Yeah, it's very interesting.
Sounds like a great discussion for dinner. I think we need to move on. Let's just take Fabio again.
Today's second speaker is Carl Haster. So Carl got his PhD from University of Birmingham, and after that he moved to CEDA as a postdoc there, and now he becomes our neighbors at MIT. So he's working on LIGO lab at MIT, and within LIGO, Carl is an expert in parameter estimation. Actually, he's a co-chair of our parameter estimation for binary mergers. And Carl's interest is mainly, well, he has broad interest, but he's gonna talk about testing of GR today. And he also has working on like a population of binary merger in the past. So, great.
Yes. So again, thanks for having me here today. I apologize for the menu bar at the top. I have yet to figure out how to remove that from these presentations.
We haven't noticed. Just the American flag.
Yes, it's my contribution. So I'll be talking to you today about two different projects. They're reasonably closely related though, so hopefully that shouldn't worry you too much. The title of my talk sounds reasonably technical, but as I'll show you towards the end, even a very technical title can come with some fairly intriguing and exciting results. So, how to validate the nonlinearities of general relativity from a population of gravitational wave observations. And as you mentioned earlier, the key word in the title is the population and what you can actually say from it. Yes. So if we want to look for effects in our observations of gravitational wave events that can be explained by not just general relativity, ideally we would look at the super loud, super clear, and easily identifiable thing in our data, say, hey, this doesn't look like anything we know about. It must be something else than GR. That has yet to happen. So far, everything we've seen is... sorry. I forgot to turn off my notifications.
As long as it's a LIGO event, that's
Yeah, that's my worry. We're not going to have that much fun. Yeah. Woo.
Quick talk. Just trying to disclose your secrets.
Yes. Cool. Yeah, so we haven't, so everything we've seen so far has been more or less as consistent with GR as we should expect. Partially because we haven't seen anything that tells us that GR isn't good enough at this point. And also both individually and also when we've tried to combine information from all our different observations. So when you try to combine information from several observations, the way to do it is to assume that the observations themselves are describing a form of a common population, and then try to infer the properties of that underlying population. This has, in previous literature and in general discussion, been called Imprint Stacking, and this is the topic of a paper that I've been working on together with Aaron Zimmerman and Katrina Tatsiani, who worked together with me at CETA in Toronto, but now we have dispersed over the world. And I think it should appear on the archive today or tomorrow. The general idea in this paper is to present the methodology in which you should think about how to combine information in an as pedagogical way as we can muster. Partially because, as we found out when we started working in this, there are a large number of subtleties and pitfalls in which you can fall. So if you think of any extension to GR as literally just that, you have general relativity and then something which adds on top of general relativity. So, and the way we parameterize this is by this dummy parameter lambda, which if lambda is equal to 0, then you have GR.
When you say add something on top, do you mean like higher order curvature terms, that kind of thing, or what?
It could be that. So the example that we used in this paper is to add in so what the effects of a massive graviton would have on these on the observations that we could have seen. But it's meant to be as generic an extension as possible.
Lambda goes from 0 to infinity or 0 to 1? What is the range of lambda?
So that depends on what the theory you're trying to test. It can be whatever you need. And so then for each observation you make, that comes with a measurement of lambda. And then if you want to say GR is appropriate or GR is less appropriate, the way to do that is by the construction of the base factor, which is just the ratio of the probabilities of GR being good at describing your data and not GR being good at describing your data. And the way then to interpret this is to say, well, as we've already said, that lambda is equal to 0 is equal to GR. So you can rewrite the GR case as this special case of the non-GR theory, where in principle so the probability of the data given your theory is the same thing as the probability of your data given your extra parameter and your theory, where you also have some prior probability of your external parameter, which you then integrate over to give you the evidence. Yes?
Could there be a more general class of models where lambda for a certain set of values is reduced to GR, but then doesn't outside of that?
Yeah. Yeah. So and in principle, so I'll come to the few different well, extremal cases in how to treat this information, and then go to the more general case. Well, mention the more general case. So, if you want to generalize this statement to multiple events, you should then think about how your extra parameter behaves when doing this extension. So in principle, the GR case is easy, lambda 1, so lambda for the first event is still 0 because you think this is GR. Lambda 2 is also 0 because you still think this is GR. And on the bottom, you do the same thing as before. You have some probability of lambda, probability of lambda 1 and probability of lambda 2. But the key thing to keep in mind is how those two parameters are connected. And I'll just talk about this more in detail on the next slide. But this factor here is the thing that is often overlooked and can mess up your analysis if not treated properly. So, the cases that I'm going to discuss briefly are the case of independent parameters versus universal parameters. So, case 1, the non-GR term that we have is exactly the same for all events that we observe. So in this case, the case with the massive graviton is a good example of this behavior. If the graviton exists, to start with, and has a mass, that mass should be the same across the universe in the simple graviton model, I guess. And if you want to fold in the effects of said graviton mass into your gravitational wave description, the effect should be the same if you try to then infer the mass of the graviton. So the probability of the graviton mass for one event given the graviton mass of the other is just a delta function. They must be the same. So in this case, to construct the space factor, you effectively you can treat your information you've gained from the first observation as just a nice and helpful prior probability for your next observation. So in practice, you compute some likelihood distributions, you multiply them all together, and that then becomes your joint posterior distribution. In the other extremal case, where the non-GR is completely different from event to event, which has a less easily describable analog, this dependent probability separates out very nicely, because the probability of lambda 2 given lambda 1 is just the probability of lambda 2. So in this case, to construct a base factor for more than one event, you just compute the base factor for one event, compute the base factor for another event, multiply them all together, because things separate out incredibly well.
But what kind of correction to GR do you have in mind when you speak about the second base?
Nothing really. So these two are meant to be very extremal.
So all kind of higher curvature corrections are the first case, right? Just another term that you're adding to the Lagrangian?
Not necessarily, because the corrections could also, in principle, depend on the specific source that is emitting the signal. In principle, max.
Like if the coupling constants are different in different places in the universe.
So if you have the solar type mass that you see in LIGO, the impact that one source can have on the gravity should be very negligible, right? Because you want to say that the structure of the universe will change after one event?
No, but lambda 1, lambda 2 here don't have to be fundamental constants. They could be a parameter that deforms the waveform in some way, and we don't know how that depends on the masses and the spins and whatever of the source. So that's one example for case 2 here, which is actually quite. It's easy to imagine that can be true, right? If you don't parameterize it correctly, you would see a modification of GR that depends, changes from event to event. But just because you are measuring a quantity that is a function of some fundamental constant and a mass and spin and so on, and each source is different.
Yeah, so the case 1 and case 2s are not necessarily required to correspond to any actual theory of gravity. So for now they're used as extremes in how to combine information. And then most actual extensions would lie somewhere in between these in these cases. So in keeping it light and breezy, so if we want to show how this behavior or how these different cases behave, instead of simulating loads and loads of gravitation wave signals and analyzing them, let's make it simple, and say that the data we have is just some noisy Gaussian data, or noisy data which had some signal in it which corresponds to a Gaussian in some parameterization. So the probability of the data given this parameter lambda is a Gaussian with a mean of mu and a sigma of sigma, where lambda can then be varied in ways which then highlight the ideas we want to put forward. So remember, if lambda is 0, GR is correct, and the base factor that we're showing here is the base factor in favor of GR being correct. So if it grows, then we think GR is appropriate. If it shrinks, then we think something else is a better description of our data. So the green is lambda is equal to 0 plus some some noise with a relevant scaling. And as you see, initially it follows this analytic scaling of square root n pretty nicely. It fluctuates down a bit because there's noise. Noise pushes our inference around in some ways. But overall, with a sufficient number of observations, we generally tend towards this analytic behavior. If we take this mu here to be 1, so I think that in principle should be lambda equal to 1, then we know that does not correspond to the appropriate behavior for GR, or it doesn't correspond to GR. It corresponds to the appropriate behavior for this analysis that we're presenting here, where the different parameter, or the parameter which defines the non-GR behavior, is the same for all events. So in that case, you should expect the non-GR base factor to shrink according to this scaling, and it does. Again, modulo scatter from noise. The interesting thing then comes with this pink example, where instead of keeping the extra non-GR parameter as a fixed thing, we allow it to vary in a range which is on a similar scale to the noise scatter. And then it grows very nicely, telling us that GR is absolutely correct. So this is an example where you need to know what the question you're actually asking is. Because if you're asking the question, I think all my non-GR is described by this behavior, and I do this test, and I find that GR is the appropriate theory, where it actually isn't. And so let's look at case 2. So again, in this extreme, I assume that any extension to GR is specified and quantified by one additional new parameter for every single observation that I do. So the analytic scaling for both GR being correct and GR being wrong are different from before. it's a much stronger scaling, so that's nice, because I can gain information much quicker this way. And again, GR scales somewhat okay according to that scaling. It's not as quick and as following the same scaling as we would like, but that's purely because of the noise. If we were to remove the noise and we do the plot, we get the green line to follow the dashed line completely. However, well, so also again, so here we draw the non-GR. If in the purple points, if we draw the non-GR parameters from this wide range, they're not going to be the same for 250 events. So in the purple case, we very nicely follow the appropriate non-GR behavior. But again, we can not be as nice to ourselves as we should, and follow the pink line, which clearly, which tells us that, well, based on the scaling, it follows GR. It even follows GR closer than GR itself. So if we approach the problem we wanted to look at this way, we would easily be fooled in saying, hey, we have confirmed very strongly that GR is the right theory. There's nothing hidden in here. So, to finish up this first section, if you want to infer properties from a population and try to gain evidence about that model, you need to be incredibly careful what question you're actually asking. And the study we're presenting in this paper can appear to be a bit on the nose in some sections, but that is mostly because we wanted to be extremely clear about all the different subtleties that we've ourselves found ourselves being confused by initially. But the important statement from this is that if you have two different theories of GR, which appear in different ways, you cannot actually test them simultaneously in a model-independent way. So if you want to do more than one test, you need to specifically say what your theory and or theories are. So I realized that I might be slightly short on time, so I'll skip ahead to the actual validation of the nonlinearities in GR. So if you have an observation of a binary coalescence with gravitational waves, the main way we gain inference or information about that signal is by knowing the phase evolution of the gravitational wave signal that we see. And an easy way of expressing this is through a Taylor series of this post-Newtonian parameter u, which is just a unitless parameter which defines the orbital velocity of the binary. And the way this is quantified is by a number of parameters, where most of the physics is hiding in these coefficients phi I, which then contain the information about the masses of the two compact objects, the eventual spins they have, and also any other internal physics that can hide within. So if you want to test these, if you want to test GR to see if it's correct, what you can do is you can say that I'll perform a test where I say that for each of these coefficients, I'm gonna extend them to be the actual physical coefficients that are defined by many years of looking at GR in various analytical forms. with some extension where I allow these phase coefficients to vary in some scale-free way. And this has been done in many different ways. So these are results from the first gravitational wave detection paper, or the testing jar companion to that paper. And the thing I want to highlight here is that if you look at the red distributions, they're reasonably constrained. They all contain 0, which is the appropriate value if GR is to be correct. And the extension, or these posterior distributions extend not very far in the allowed range. So I think for all of these 5 parameters, they were allowed to vary between plus minus 20 or 30 or so. Then compare that against these turquoise distributions, which cover the entire range that is shown, and they cover the entire range that is not shown as well. Which then mean so for the red ones, the analysis was done such that for the phi 0, you allowed this parameter to vary, and kept every other parameter, or every other phase extension fixed to the GR value, and then you repeated that, well, however many times you could. And for the turquoise one, you allowed everything to vary at once to see what you could learn from varying everything at once. And the conclusion is that if you allow everything to vary at once, you don't learn very much, because you have too much freedom in your parameter space. So I wanted to find some universal parameter among the PN facing terms to see what could be learned from them. So on the screen in front of you, you have a small selection of the PN facing terms. And then I invite you to find something that's common between all of these. So I should say that the eta corresponds to is a quantity representing the mass ratio of the binary. The SL and sigma L give you information about the spins. The gamma PN is another combination of all the intrinsic parameters and so on. But one thing that's common between all these is this quantity pi. So this is the somewhat initially not very clever, but at the same time quite clever, insight that pi isn't necessarily a... So if I assume that I don't know really what pi is, I know that GR predicts that pi should be the value of pi, but if I want to be slightly more ignorant than that, I can try to measure pi. And the reason why this is actually irrelevant as to do, is because of how pi appears in these facing terms. So back in the 90s, when they were initially derived, in the way that these the coefficients were derived, it was found that when you write down the luminosity, or the expression for the luminosity of the gravitational waves for a binary in spiraling binary system, those expressions contain, or those coefficients contain expressions like this, where lambda in this case is this complex number, and omega 2pn. So in this case, I'm just showing the second post-Newtonian coefficient, but it's the its frequency. And if you have some expression where you have a log of I frequency, like you do in here, you can write that as a log of frequency plus I times pi over 2. This is very much a complex number. The luminosity needs to be real, so you write all of this out, you multiply all of it together, you keep the real part, some of these pi's remain. There's also one pi squared term which crop up in the from the binding energy, not luminosity, but it's also in the tail term, which is important because that means that if I want to look at pi, I'm normally testing how valid the expressions governing the nonlinearities of this phasing series, if they behave like they should. So, if pi is a parameter, that means that I can include it in my parameter estimation analysis. This is just a description for the specific waveform model that I've used. It carries within it this phasing series, so it's a good thing to do. We have 11 detections so far, so let's use all of them. I've done more or less the same analysis that we did for the actual detection analysis that was presented in the first transient catalog LIGO produced. And then I allowed pi to vary between plus minus 20, just to see what I got. And this will appear in a few weeks in a paper. So just as an example of how parameter estimation looks in the end, is you can look at this massive corner plot where the little teeny tiny squares in this case, and the distribution tells you something about what the binary parameters are. So doing something like this takes normally a few days, plus minus a bit. So I spent a few days waiting for my pi results to appear, and eventually they did. So I have 11 individual measurements of pi, where some of them span the entire prior range, where the prior is shown as this gray band at the bottom. And then in this zoomed in version, or a zoomed in plot, I then show the section around where pi true is. And I should also say that whenever you see this dashed line in this plot, that's where the true version, or true value of pi is, or the value of pi that the rest of maths tell us is, I guess. Not surprisingly, the observation of the binary neutral star is the one which gives me the tightest constraints. That is to be expected, since what I'm measuring is how well the in-spiral part of the gravitational wave agree with GR, and this was by far the longest in spiral. But, remembering what I told you earlier, if you have a parameter which you inherently believe and can argue for, should be the same single parameter across every single analysis you do, you are justified to combine them all into one global measurement of pi. So in this case, as you go from light blue to dark blue, I add more and more observations to this measurement. And so, and also here is to highlight, well, partially how important the binary neutral star is, but also the fact that the 10 binary black holes don't do terribly on their own. So if I have a posterior distribution of pi, I can actually present how my measurement of pi is pretty good. And so if you compare this measurement on how, so with the other measurement of these deviation or phase deviation terms that LIGO produced before, this is determined to a higher precision than any of those that we've published so far. Also, since the pi can be everything theory is literally a extension to GR, right? We know the value of pi. It is very easy to compute a base factor in favor of GR just by taking the ratio of the prior, which is barely seen in this plot, and the posterior value or the posterior distribution at the value of pi true. And that tells me that I favor GR with a base factor of 330, which is not super high, but it's still a respectable base factor. So I'll go through the last remaining plots very quickly. I've also checked how well my analysis does when I literally look at garbage signals. So this is real data, real noisy data, where I'm looking at background triggers. So where the data between the two LIGO detectors have been shifted in such a way that nothing that's as pinged up as could be a signal is actually a real gravitational wave signal. It's most likely just two noise blips matching somewhat with each other. So when I do this, I get pi results that are all over the place. If I try to combine them, I get a value of pi which is largely wrong. But in this case, for this specific background analysis, this is what I should expect. I don't think, and nothing in here should be described by GR, and I find that it isn't, so that's appropriate. I can also check how well my analysis is against other real non-GR effects. So similar to what I mentioned before, I can add in the effects caused by a massive graviton. So in here I quantify that by the different values of the graviton quantum wavelength. So if the graviton is massless, I recover this blue distribution, which is nicely centered around the true pi value. It's slightly offset, but that's fine. So I should also say this is the joint analysis performed on simulated signals that correspond to the first 3 binary black hole detections that we made. If I add in a small effect of the massive graviton corresponding to the current bounds we have from LIGO and LIGO, it's a small shift. It's not very big. That's fine, because what that bound has told us is that we haven't seen anything really. If I add in a super big graviton, so with a very fairly small quantum wavelength, I can recover anything. At that point, my model isn't really good at describing what it should be. And if I add in something in between, I see a shift in what I think pi should be. This is not meant to be interpreted as a way of quantifying or justifying non-GR being there. This could give you an idea that what you're looking at is not appropriate, but there's no way you could arrive at this conclusion for this pi distributions and say, hey, I must have a massive graviton in there. In this case, I know that's the cause, but that's because I put it in there myself. So, to finish up, I know that me and everyone else can perform a robust test of GR from a population analysis, but you should only do this if you know exactly the question you're asking, and by exactly, I mean exactly. You can use gravitational waves observations to measure pi. It's close to pi. And you can also use that measurement to then make a direct validation of the nonlinear terms in general relativity. It's nice because it's doing so simultaneously at 4 different PN orders. I favor GR with a base factor of 330. And it could help to identify, but not characterize, other non-GR effects. And with that, I say thank you.
Yeah, so this is very interesting, and now thank you for letting us know what pi is. But, I noticed there was a bias in the distribution for pi. So it wasn't around pi, it was offset. What does that tell you about your measurements?
For this one?
Yeah, it's off to the lower side, right? It's not right around 3.1415. So what does that tell you about your estimation of GR parameters and biases in those?
So at the moment, those types of shifts are consistent with the presence of noise in my data. So at the moment, I'm not worried about that. So that's
well, what I'm asking is, can you learn something from it? Is there something systemic about the system that biases it lower, or is it just noise?
It's just noise, unfortunately. So when you look at the different individual ones, they are recently all peaked around the true value, and then the main reason why the global one is slightly biased towards lower values is then because the binary neutron star inference is biased towards slightly lower values, and that's the dominant provider of information at the moment. But I would expect with the hundreds of events we're going to see in the next observing run with LIGO, this should hopefully average out a bit more.
So, the first half of your talk, there was that magenta line which misbehaved, right? It should have gone down, but it went up.
Yeah.
Even though it was not GR. But you designed it so that the deviation from GR was small, right? Mu is 0.1. But still, one would think that given enough data, this guy should be able to tell that GR is wrong. So is that line finally with large enough N going to come down?
No.
No. So what's going on?
So the pink line here is not ever turning over when performing this test. But if you were to compare the case 1 and case 2 and how, in these plots, green is always GR is correct, purple and pink are GR is wrong, but they're wrong in different ways. Purple is the one which follows the assumption of the test. Pink is the one which breaks that assumption. And since the tests I presented are opposite and complementary, the behavior of the purple points in this line, or in this plot, is effectively the same as the pink one in here. In the sense that here I draw my non-GR parameter from a uniform distribution across some span, and it tells me that GR is correct when I do this test. Here I draw my non-GR parameter from a uniform distribution across a fixed span, and it tells me that GR is wrong. So if the non-GR parameter were to behave in this way, so being drawn from a uniform distribution with a known span, then the test I should be doing should be this one. And conversely, if it's a universal parameter with a known and fixed and true value, then I should always be performing this test. But in reality, as we discussed a bit earlier, most extensions of GR don't really correspond to either of these two extremes. So the way one should do it is then to, which we also describe in the paper, but I skipped it in the presentation, is to think about the non-GR parameter being drawn from a separate distribution with some known parameterizations, and then you can then build up your evidence under that assumption. So instead of trying to measure the non-GR parameter itself, you would try to measure and characterize the parameters of the distribution from which your non-GR parameters would have been drawn. And that way is safer. It's most likely a bit slower in gaining evidence because it's a more general theory sometimes, but it's safer overall.
Next question, Eric.
So if I understood you correctly, the case where you're allowing lambda to vary from event to event, that's both, you said that maybe either is a deviation from GR as a theory, but also possibly because of dynamical peculiarities of the individual events. Is that correct?
Yes, I guess.
Okay, and if that's
But
correct,
I should also say that that was not like main justifying for this.
but if that is correct, how do you distinguish between in that case whether you're testing whether GR as a theory is correct or whether just the models that produce the waveforms are correct? They're not capturing some of the correct dynamical behavior of the actual events.
If we have enough events, we can tell, I guess.
Yeah. For some tests, apparently not.
Yeah, well, so I think.
Oh,
never.
Never.
He says you can go to n equals infinity, this fellow will never tell you that GR is wrong.
If you assume that
Under
the behavior
these
is
conditions, yeah, no, I
yes.
understand.
So I think in practice, testing for something that is not GR and testing whether your model is appropriate is largely the same thing. In the sense that when we say that we compare against GR, we always compare against approximations to GR, which we know are missing some features. Hopefully those features are not too big to bias our results, and that assumption is fine for everything we're doing now. In the few years down the road and a decade in the future, this will no longer be the case. So at that point we could be wildly dominated by really uncontrollable systematics that pushes us in every direction. But in practice, looking for non-GR and looking for model wrongness is the same thing for now.
But you improve your model. So
You have better
models.
So when you get the better model, you should do the test you have done before to see if you get the same results.
So it seems to me you can have cases where you parameterize care and you look at variations from care and ask for that as deviation from general relativity. Or you could have something like heavy gravitons and then say what the effect might be. But a third might be to say some phenomenon like departures from no hair and then ask for different causes. I mean, there are different models for how you could deviate from no hair, right? You could have soft hair, you can have heavy graviton-induced departures. So if you ask sort of phenomenologically from the point of view of deviations from soft hair, it actually gives you a kind of sort of a branching set of assumptions in order to make it tie to this kind of analysis.
Yes. So at that point, what you should do is, so what you need to do under this formalism is then to identify all of those branches and specify preferably specify what the model would be for each endpoint of those branches, and then test them all, and then.
That's what physicists do.
Yeah, no, exactly. But
that's our job description.
Yeah, no, but the tricky thing is to not then try to say, I'll describe all of them with a single unified modification, because that way, with that way you could easily find yourself with a pink line instead of the purple.
Actually, Peter, this comes back to what we have been discussing in the philosophy discussion, right? I mean, we're doing Bayes.
Right.
GR is well defined. Question is, what is non-GR, right? The world of non-GR is really not defined. Within one parameterized description, you can have a lambda, or it could be the quarter pole, or some, the 16th pole, whatever.
Yeah.
But the overall space of non-GR is not something that we can even comprehend. So that quantity that you normalize by for your whole Bayes calculation, that integral over all the lambdas, that is where I think one has to hardwire some limitation on what is the question you're asking.
Yes.
And so when you say violations of no hair theorem, how do I test? You can only test particular
Right.
families of violations, not all possible violations.
That's exactly why it bothers me when people say we're gonna test the no-hair theorem.
Right.
They're not, they're testing some realization of that assumption.
And that's fine.
That's fine,
Yeah.
you just have to be clear what you're
Yeah.
doing.
Right.
But the same thing happens in cosmology, for example. There is Gaussianity of the density.
Yeah, and what is non-Gaussian?
And non-Gaussianity can be anything, and there could be various reasons for it. Either inflation is wrong, or something, you know,
Right.
and or a phase transition. So it's exactly the same situation.
Yes.
Dog versus non-dog.
Exactly.
You have one thing going for you though, insofar that that there's very few modifications of GR that actually make sense.
Right.
Well,
So-
yeah.
Let's thank Carl again.
Let's take the 500 string theories, and they're like, no, but those are
They're all
those are
gonna
those
be
are
No,
extensions of theory, right?
When they think this way, right?